Yesterday we started doing Gaussian picture. The picture of the collision, space-time picture of the collision of electrons. I showed you theorem. How do the Partons distribution localize as a function of Gaussian picture? That I showed you yesterday. So we found that most abundant species are the Gluon inside the proton.
Hello.
What are these integrals? Values of the integral? X goes from 0 to 1 because it's a fraction. This is U valence quarks in the protons integrated over all fractions. What do you think the answer will be? Because there are net two U quarks. And that's the difference between number of U quarks and number of anti-U quarks. And this will be 1. In the case of neutron, it is opposite. This will be 1 and that will be 2. V partons are the partons with very low values of X. That are, in other words, very slowly moving partons. That's just a nomenclature. These are the numerous low X partons in the nucleon. And because of the Lorentz contraction, these valence quark distributions, they shrink. Because of the Lorentz contraction, the longitudinal spread of the valence quark wave function is expected to be 2r upon gamma. Gamma is the Lorentz factor. And since gamma is very large at rate or let's see, this is very small. However, Gaussian has shown, and I'm not going to show it here, that although valence quarks distributions are shrinked, that does not mean that the nucleus is, the whole nucleus can be shrunk to, if gamma is 100, this is an extremely small number. But that doesn't mean the whole nucleus gets shrunk, because no matter how fast the nucleus is moving, there are always some partons which are slowly moving attached to it, because that is the basic QCD scale, lambda QCD. So lambda QCD, if you take the inverse, you get about a 1 Fermi. So the nuclear size cannot be shrunk below 1 Fermi. Ken showed that no matter how no matter how high the beam energy or gamma, incoming nuclei always have in them the partons with typical momenta P, which is lambda QCD. So the longitudinal spread will be about 1 Fermi. So in a direction, in the transverse direction, it's okay, I think. So the collision of two ultra-relativistic nuclei can be looked upon as the collision of two clouds of partons or clouds of V partons. And as a result of this, a highly excited matter with a large number of virtual quanta is created in the mid rapidity region. Mid rapidity means near y equals 0 in the center of mass frame. You can also look at this as very strong color electromagnetic fields. a strong strong chromo field. Color electric and color magnetic field. So this is the first thing that happens after collision. Virtual quanta are very strong region of very strong, very high energy density in the form of virtual quanta or coherent. Now, this has to go to real quanta. Or its coherent state becomes decoherent.
What is a coherent field?
Coherent means it's something forming a unified or one single. It's not distinct particles, not real particles, but virtual particles. Coherent just means forming a unified whole. Now this is not instantaneous, it takes time. Going from virtual quanta to real quanta, it takes time. Or same thing, coherent field getting into decoherent state takes time. And there is some characteristic time that's denoted by tau. Equation. This is the D. Okay. Another way to answer the question of what is meant by coherent is there are many partons, they are all interacting with all of them. Not to few of them in the network, but all of them over a certain region. So they are not free. They are always in interaction with many others.
So, what is the origin behind these B partons? I mean, why does this have to be of one Fermi? Why doesn't it shrink longitudinally the nucleon?
So that is what. Okay. First part question is what are B partons? They are the vacuum fluctuations. Gluon giving quark, gluon giving quark anti-quark, or quarks emitting gluons. They are very low momentum, so you can produce them as many as you like. Now you are saying why they cannot be shrunk. Okay, as suppose at some beam energy you have shrunk it to very low size, but when you boost it further, Quark has shown that new bunch of V partons are created and they are always there. Original V partons may get shrunk, but when you boost it further, more V partons are always there. Because that is lambda QCD is the basic scale, and you always have partons with that.
So at that scale, the nucleon is essentially only V partons, effectively.
Yeah. So those are the ones which will play an important role in the collision. And those which have got shrunk, they are moving with very high velocity and they try to pass through each other because of asymptotic freedom or time dilation. We'll see that in greater detail. So this is some characteristic time in the rest frame of a parton. But when the partons are moving, then this gets time dilated. Gamma times this is the time dilation. Decoherence time. Partons which are moving slowly have a small gamma factor. Partons which are moving very fast have a very large gamma factor. So fast partons decohere after a relatively longer time. They take long time to become decoherent. Slow partons decohere earlier. Now earlier means what? The system, at earliest time the system is very small. Two nuclei are almost touching each other. So if they are becoming real early stage, means they are produced near z equal to 0. Right? Those who become real very early, they are produced at z equal to 0. On the other hand, as you keep on increasing the gamma factor, the system they decohere later on. But later on means the system has become bigger. So they tend to get produced at a larger values of z. Let me write that. Slow partons emerge earlier and therefore near z equal to 0. And fast partons they emerge later and further away. So there is some name for this process. It's called inside-outside cascade. That is, it starts from inside to outside. Partons or the large X partons, they continue to move more or less along their light cone trajectory. The two nuclei are approaching each other along these lines. We are working in 1+1 dimension for simplicity. So these are the two, this is the projectile and this is the target. And the collision happens at time t equal to 0 and z equal to 0. And those which are, and after the collision, then they travel along various paths. So those which are the fastest partons continue to move along more or less along their original directions, this way and this way, and the slower ones are continuous and they are successively inside. So time dilation leads to near transfer. Yesterday we started with some figure data showing that high energy collisions are most transparent. The net number of protons minus antiprotons was very low, and this is a theoretical understanding of why that happens. Essentially because of time dilation. So if I have to draw a picture of the velocities of partons, it could look like this. These are of course not the original nuclei, they are because they get wounded as they come to each other. Let me just call it target, which is different from original target and projectile.
What do you mean by time dilation is near transparency?
That's what I was explaining, the time dilation factor gamma, right? The decoherence time. Without gamma, this is the decoherence time. That is the time virtual parton become a real parton. This is some time scale for that. But if the parton is moving in the center of mass range, that time becomes larger. That is time dilation. And because of time dilation, they tend to pass through each other without interacting.
Can we calculate this decoherence time?
It's not easy to calculate from first principle, but it's estimated from QCD scale. It could be 0.1 Fermi or 1 Fermi or less. So now, as I said there, the partons which are
Produced early are the slow partons, slow velocity.
So I can show the velocities by this. This is arrows show the velocity in the z direction. This is z.
As you move
Away from this, velocities are larger and larger. And the partons which are sitting here, they are charging with the highest velocity. And same thing on the other side. So Gaussian proposed that velocity z is given by this. At any given time, the matter that is moving has, which is located at z, its velocity has to be z upon t. When z is 0, the velocity is 0, and it keeps on increasing successively. And here it is almost equal to the speed of light. Z and t are almost the same. So this is reminiscent of the Hubble's law. There also the velocities are proportional to the distance of the galaxy with some constant. Velocity is h upon, right? This is the and you can check that this is a boost invariant prescription. Invariant. Which means if
Vz is this,
then Vz prime is Z prime upon T prime. No, this is T to standard time. T. Time measured in the center of mass range. So at any given time, the velocity is supposed to be here. Velocity is z upon that time, whatever time it is.
So the size estimate can be roughly Ct.
Size of what?
Size of the whole thing that is
Size of the whole thing?
right.
It depends on the time. It increases with time.
Like the fastest moving ones are
It
closer
will
to
be
the speed of light.
Almost, not exactly. Even initially it was not exactly speed of light, but almost. And it gets reduced, of course. But still they are moving very fast. You can also check that if you E prime gamma E minus instead will be, now what is n z prime? Gamma will be 1 upon 1 minus if that is the velocity, then the gamma factor is this, which is P upon tau. Tau is the proper time here. E square minus z square is the longitudinal proper time. Therefore, this becomes E prime is P upon tau. What is that? Square minus z square is tau. X minus 0. Matter is governed by the proper time. So, and proper time was defined as tau root of t square minus z square. So all those parts of the system which have the same proper time, they evolve in the same, they are at the same stage of evolution. So, once again, the system is in this part of the diagram. Different parts are different t and z, but if the parts, different points is at the same tau, they are at the same stage of evolution. The system evolves, right? As we saw just earlier, goes through various stages. But if the tau is the same, then the stage of evolution is the same. And what is that curve? It has constant tau. Those are the hyperbolas. These are the hyperbolas of constant. So, for example, here and here, the part of the matter that is formed here and here, they are very different t and z, but since tau is the same, they are at the same stage of evolution. let us chalk out how the system evolves. This is the possible scenario. T equal to 0 equal to Z. This is when collision happens. So of course this implies tau is 0. Then let me number these, like 1, 2, 3, 4. So from time tau, going 0 to tau 1, as we saw earlier, the real partons emerge from virtual. It takes some finite time. Let that be tau 1. So it is the formation. Tau 1 is the tau. And its estimate is about 0.1 per. That is the first stage of the collision. In time tau 1, which is same as this decoherence time, estimated to be a fraction of Fermi. It could be 0.1, it could be more than that. We don't know the exact value. But that is the first thing that happens, formation of Gluon matter. Next, that means you are now here on this hyperbola. Then tau 1 to tau 2. This matter, which is not in equilibrium, it is likely to attain local thermal equilibrium during this time. There are enough number of collisions happening. So, local equilibration. Tau 1 to tau 2, local equilibration of Gluon matter happens during that time interval. That is same as formation of. Of course, provided the interactions are strong enough and enough number of times they collide. So this tau 2 is also denoted by tau thermal, that is thermalization time. And it is again various calculations show that it's about a percent. At this time, temperature is several hundred MeV. Let's say 300. Depending on your initial energy. At rate, it could be maybe 350. At LHC, it could be 500. And at higher LHC energy, it could be even higher. So this is the corresponding temperature when the system thermalizes. before that, from 0 to tau 1 or earlier than tau 2, you cannot even talk about temperature because temperature is an equilibrium thermodynamic quantity. So this is the initial temperature. So in a sense, now this is the stage where fluid is formed. Fluidization has happened. Fluid by definition is, okay, fluid is something which is now in equilibrium, local equilibrium. So this is the point of fluidization.
So what is the order of fluctuations in temperature?
Fluctuation in this value.
Because since it's in a local thermal equilibrium, so this is the average, right? These numbers are actually fitted. We don't know what the numbers are. By making detailed calculations and treating this as a free parameter, one tries to determine it. Now there are large uncertainties in this. There is not a very sacred value. And this field is active, these numbers are being calculated, determined, so it's not yet finalized. So what will be the theoretical framework to describe that process of equilibrium? Can you use hydrodynamics there? During this stage, can you use hydrodynamics?
So I think what he was trying to ask was is probably confused by this use of local thermalization. You're saying local thermalization, and then you are mentioning one temperature T.
Yeah. Okay. What this is, the temperature, initial temperature, of course, is also called initial, and at the center of that disk in the transverse plane. So that is the maximum temperature that you find at the center, and of course it is less as you go away from this because the nuclear density goes like this. Rho as a function of R is the maximum density at the center. The highest temperature or highest energy densities are reached at the center, and that is that value. And it decreases as you go away. And this again is an idealized picture. I showed you some figures yesterday. Actually it is not smooth. There are lumps here and here. So there are higher spots of higher temperatures and lower temperatures. But this is an ideal picture. So I was asking, what is the theoretical framework to describe this process? Can you use fluid dynamics? You cannot, because fluid dynamics is a framework which works only at equilibrium or near equilibrium. Now you are not yet at equilibrium. Only after tau 2, system has reached local thermal equilibrium. So only afterwards you can use fluid dynamics. Until then, there is some other framework, which is the framework of kinetic or transport theory. Take transport theory. Okay, so now we have gone up to tau 2. Let's go ahead. Tau 2 to tau 3. Now you are allowed to use hydrodynamics. This is hydrodynamic evaluation of QGP and then appropriate equation of state. Because the degrees of freedom we know are Partonic, so equation of state will be Partonic equation of state. And what will be tau 3?
tau 3 will be, how long can you keep on doing this with this equation of state? Until you have reached that crossover point. Because if the temperature goes below that, then that equation of state is not valid. You need some other equation of state. So tau 3 corresponds to temperature, which is about and this is when the hydrogenation when you go through that temperature crossover region, hydrogenation takes place. That is, partons combined into hadrons. Next, from tau 3 to tau 4. Now you have hadrons, and if they are in equilibrium, local equilibrium, then you can continue using hydrodynamic framework. Of course, it's an appropriate equation of state. So you can still use hydrodynamics. Hydrodynamic evolution of hadronic matter. And it's supposed to be in equilibrium, or if it is in equilibrium, and with the hadronic equation of state. So that is the end. After this, you cannot use, now system has gone out of equilibrium at this time, tau 4. You cannot use hydrodynamics any further beyond time tau 4. So in other words, that is when it's no longer a fluid, but it has become, density has become so low that now you can talk about particles. So this is the stage of, sometimes it's called particleization. Just as this was fluidization, some people call this stage particleization. Now, not a fluid, but now it's a particles. Particles means these are hadrons, mostly pions. So we have gone up to tau 4. Now once again you can use transport theory here, relativistic transport theory.
The system is then rapidly cooling out.
Yes.
What is driving this coolization?
System is, the whole thing is expanding because there are high pressure, high energy density region in this fireball, so it expands. Because outside you have vacuum, a region of zero pressure. So that is driving the difference of pressure, which is driving the expansion. And when the expansion happens enough, you cannot describe it as a fluid. It becomes distinct particles. So this is the transport theoretic evolution of matter, which is out of equilibrium. So this corresponds to approximately temperature 150 centigrade. Again, these are all fitted numbers and not very sacred numbers. It depends on what model you are making for simulating the whole process. So this is approximately 150 MeV, and so as the system expands, first the inelastic collisions stop, and later on elastic collisions also stop. So this is where we'll assume that the inelastic reactions have stopped. So this is called chemical freeze out. So inelastic interaction stop. Which means the abundances of various particles that gets frozen. Freeze out means something is frozen. What is frozen? The ratios of various species. How many pions versus how many kaons, etc. Those ratios get frozen. They don't change anymore. That's why it's called chemical freeze out. Later on, the elastic collision stop. Once the elastic scattering of collisions stops, their energy momenta gets frozen. Right? So the particles are not even interacting elastically, their energy momentum cannot change. So that is what is called kinetic freeze out. Kinetic. And it is approximately again 110 or 120 MeV.
For this transit temperature, kinetic theory is still valid?
Yeah. Until then, kinetic theory is there. Same framework here. And after this, there is a free streaming. There are no more interactions. The particles just go straight to the detector. Not straight, they are magnetic fields, they don't travel straight, but they are free and they go to the detector.
So,
Yeah.
so how do we know in stage 4 whether or not the hadrons are in equilibrium? Because if I perform the experiment, I just see the particles. I know that, okay, at T3 it's in equilibrium, more or less. And then I know that it's going into hadrons. Now there's a big jump because I don't know how the evolution is actually governed.
Right.
I don't know how it's going out of equilibrium, whether it's going out of it or not. At the end of the day, I just see the chemical freezer.
Right. So if the hadrons are not in equilibrium, then these two times will collapse.
Oh.
Tau 3 and tau 4 would be the same.
So, but how would I tell
Yeah.
in the final?
Okay. Again, you have to do the detailed calculation with some equation of state. The equation of state that are currently used is something like this. What the thing is? Energy density as a function of temperature. You are starting somewhere here, high temperatures, and you are going this way. And this, suppose this is 155 crossover temperature. And as you travel here, up to here, this is Partonic equation of state, and here Hadronic. So the state-of-the-art equations that are available today, they fit up to some point here. So it's being assumed that even little beyond 155, and as I said, the difference is not much. This was 155 temperature, this was 150. Did I write that? tau phi was so after tau phi, tau 4 to tau phi. So this 150 would be here. So it's being assumed that only from 155 to 150 system may be in equilibrium. But again, these numbers are, this is well determined on lattice, but this is the fitted number. And equivalently, these times are also in a sense fitted. The temperature is being fitted, so effectively you are fitting, adjusting these times.
So in any fitting, do I actually need that interval tau 3 to tau 4?
Yeah.
You need that.
Yeah, you need that.
So if you omit that, you will see that it doesn't.
Some effect, fit is not so good.
I see.
Sir?
Yeah.
You just said that the temperatures have very large error bars, right? So isn't phi MEV gap too small to be detected?
Yeah, it is right. It is, don't take these numbers very seriously. As I said, this is a possible scenario. So free streaming to detectors. So as I said, this is a simple-minded picture. Okay. This is a possible scenario. And all right, so let us go ahead. So that is the end of the description of the Gaussian picture. Now I will make some remarks about present some results. Because we are going to need this later on when we do fluid dynamics. So let us try to recapitulate some of these results. This is the well-known result from thermodynamics. Now what is U? Internal energy. Number of particles. But now there is a difference between relativistic theory and non-relativistic theory. In a non-relativistic theory, normally the internal energy does not include the rest mass. While in the relativistic case, the internal energy includes the rest mass, and if you take start here and take a non-relativistic limit, that rest mass energy will appear explicitly, which is absent here. So even if you take a limit, it may not agree with this because of the existence of the rest mass in this case. normally does not include the rest mass energy. Here it does. And the non-reducing limit is taken, it appears explicitly. There is another difference between relativistic theory and non-relativistic theory. When I asked you what is n, you said it's a number, which is true here. N is the particle number. And is conserved. In the relativistic theory, numbers are not conserved. You can create particle-antiparticle pairs. So, in this case, when you write n, it does not mean particle number, but it means it could mean baryon number, which is conserved, or charge number, which is conserved, or in case of strong interactions, it could be strangeness, which is also conserved in this strong interaction. So n is not a number in the relativistic case, but is conserved quantum number. Let me write somewhere else. Difficult to write here. Difference between relativistic and non-relativistic thermodynamics. Now again, this is something you know. U, the internal energy, is a function of V, S and N. It's a homogeneous function of these variables. If you multiply of degree 1, so if you multiply by lambda, you get lambda times. And if you differentiate with respect to lambda and put lambda equal to 1, you get this relation. Called Euler's identity. You will know why I am doing all this, which you are supposed to have done already. But this is called Euler's identity and relates 7 thermodynamic variables.
if you take du, you will get 6 terms, right? Out of those 6, the 3 of them, sum of 3 vanishes because of this. So do this, there will be 6 terms. Then use that relation, which will give you VDP. This is called Gibbs-Duhem relation. It shows that the 3 intensive variables, pressure, temperatures, and chemical potential, are not independent. This is the relation between those 3. Three intensive variables, namely pressure, temperature, and mu, are not independent. These we already derived, these 3, but one also defines the enthalpy, H is enthalpy. Also called heat function. Enthalpy or heat function H is defined as U plus PV. And you can see from here it is Ts plus mu n. But in the fluid dynamic equation that we are going to derive later on, this is not what is used, but the similar relations with internal energy, one has internal energy density. So let's divide this by volume. So what will you get? It will be epsilon U. Epsilon is the energy density, internal energy density. Temperature and S becomes small s. This is minus P and mu n. Simply dividing by the volume. What about this? This will give a small s dt, dt, and dv. Now, these two together give you this. Similarly, these two can be used to obtain this.
We did this earlier by taking differential of this, we had 6 terms, and using this we got this. Similarly, take differential of this, you will get 5 terms. Out of those, 3 will vanish, sum of 3 will vanish, and 2 remain. D epsilon is T ds plus mu d. Enthalpy density, this is energy density plus pressure, temperature, and entropy density mu n. These two were used to obtain this. Similarly, you can use this and this. So, all this part of this diagram, these are needed in fluid dynamic equations. So we don't need them right now, but this is a good point to derive them once and for all. These are needed for a fluid dynamic equation. Very often there is no end. For example, at LHC, the energies are so high that there is no net baryon number. Almost equal number of particles, quarks, antiquarks, or particle antiparticles are created. So n vanishes. Then this becomes, if n is 0, you can write down similar explanations which are much simpler than this. Thermodynamics of Gluon plasma. Before that, some preliminaries. Yes. You know that you if you recall this Boltzmann factor, e raised to minus beta e, and we are talking about temperatures which are, let's say, 200 MeV or of that order, then only these 3 are relevant. And these will be ignored. Down, bottom and top, we don't need them. Strangeness also is sort of on the borderline because its mass, roughly 100 MeV, is also very comparable to this. So this is on the borderline, but these are very small, less than 10 MeV, around 5 MeV. So these are the relevant ones. Sometimes S is also ignored, but often it is also included. We'll be using this fact while studying thermodynamics of UGP. We'll ignore interactions. Interaction among quarks, gluons will be ignored.
for this purpose. However, we'll assume equilibrium, just like in an ideal gas. There are no interactions, but the system is assumed to be in equilibrium. You already are an expert in calculating number of degrees of freedom. I've seen a few times in the tutorial. How many quarks, gluons, etc. we need to worry about, depending on spin factor, color factor, flavor factor. So that I'm not going to do. So you can calculate Ng. Factors of Ng or Quark. Spin factor, then color factor, and in the case of quartz there is flavor factor. Going to assume grand canonical ensemble. So quantities that I'm going to present are ensemble averages. Energy density or number density, etc. They are ensemble averages. And I think this also you have done. One result. Energy density per degree of freedom for massless bosons. Have you done this in some of the course? Epsilon E is pi squared E4 upon 30 per degree of freedom. There is this exercise for the tutorial so that mu q is minus of q bar. Quark and anti-quark chemical potentials are equal and opposite. So that is the tutorial problem. So we'll assume that in the rest of the talk. Energy density per degree of freedom for massless fermions and antifermions. Have you done this? So there is a tutorial problem corresponding to this. Let me just write the result. Epsilon F plus epsilon F bar. Have you done this with chemical potential or without chemical potential? Without chemical potential. Okay. No. Let me write this expression.
is for fermions. And antifermion will have, instead of minus mu, there is a plus mu. Now this integral cannot be done analytically. In either of the two. There are two integrals, one for epsilon f, other for epsilon f bar. They cannot be done analytically, one by one, but the sum of the two can be done. And that is the tutorial problem. So, epsilon f. Again, if I remember, this is per degree of freedom. So try to do this. And once you have the epsilon b and epsilon f bar, by multiplying by suitable degrees of freedom, depending on color, flavors, etc., you can calculate epsilon for Gluon plasma. So that is also one of the exercises in the tutorial. So I will stop here, and next time I will talk about number density. So this is all energy density. And also do similarly number density. Any questions?